Okay, so we're recording. Okay. Good morning. We'd like to thank each and every one of you for coming out for the AIAU forum for today. Today we have with us Dr. Denney. He's going to be talking about quantitative techniques and cardiovascular MRI. So if you would, please join me in welcoming.
Thank you all for inviting me to give this talk. I've been looking forward to it for a while. It's very excited about being here. I'm in the Department of Electrical and Computer Engineering and also direct the MRI Research Center, which y'all may have heard about. We're in the Research Park, which is down South Donnellan, where it intersects South College Street. About 90% of what we do is brain imaging, and we've got a lot of interest in that. We've got tons of data that we've collected over the years, brain data that need analyzing, and AI is a great opportunity for doing that. But anyway, that's a separate talk. Today I'm going to talk about. I'm actually I'm actually a cardiovascular person by training. I'm a heart guy, so we're going to talk today about cardiovascular MRI. We do cardiovascular MRI at the MRI Center. We've done several projects around cardiovascular MRI at the center. Most of the data here today is going to be data I collected at UAB. That's where the patients are. But we do. I'll show some of the data that we collected here. I'll be sure to let y'all know what that is. Okay, so what we do in my group is we develop advanced techniques for diagnosing valve disease, heart attacks, diabetes, hypertension with cardiovascular MRI, and other things as well, pulmonary hypertension. We'll talk a little bit about that as well. Most of my work has been funded by the National Institutes of Health, a little bit of funding from the pharmaceutical industry and some other sources. And almost all the work here I do is in collaboration with the UAB Division of Cardiology. I've worked with these guys for a long time. They're super collaborators and good friends of mine, and we've worked together for a long time, and we've worked really well together. So I'm going to talk today about quantification of new parameters. So when you do a cardiovascular MRI, it's actually pretty rare in the cardiology community. Most imaging of the heart's done with ultrasound because it's a really cheap modality. You can do it at your office. You can buy, if you're a cardiologist, you own the Echo machine, and you can get reimbursed for that instead of having to get somebody else reimbursed for it. But it is becoming much more common. It's increasingly more common to have cardiac MRIs. I won't really go into the advantages of that, but when you do a cardiovascular MRI scan, typically you're looking to quantify cardiac function. I'll talk a little bit about what that is. There's some advanced techniques that we use. We can quantify mechanical function in the heart, strain in the cardiac muscle. Then also we've done some work, and we're doing some work now on quantifying pulmonary artery stiffness. I'll talk a little bit about that. For each of these, I'll motivate a little bit the clinical reasons why we're looking at these problems. AI is taking over this field like it has every other field on the planet. So we use machine learning in most of this work, particularly in the function and geometry and the pulmonary artery stiffness area. Not currently using it in the mechanical function. That's on our list to do. We just haven't gotten to that yet. I'm by no means I'm an AI or machine learning expert, so definitely look to y'all to give me some feedback on the things that we're doing, and welcome y'all's comments and suggestions. I definitely come from a math and physics, image processing, computer vision type background. AI is still relatively new to me. Very exciting. I mean, there's been problems, and I'll mention these. We've been beating our heads against the wall as a community for decades trying to solve them, and AI came in. And, this is not the only field where that's happened. But anyway, we'll start off with function and geometry. And this is some data that we acquired at our MRI Research Center. This is a typical cardiac MRI scan. When you go get it, if you do get a cardiac MRI scan, they're probably going to get one of these. And this is, we call this a cine MRI. Cine is the same root word for cinema. It's a movie. We acquire a movie, the beating heart on a slice like this. We cut, so the heart, the left ventricle, this is the left ventricle here. That's the right ventricle. And the blood's being pumped out, as you can see. The left ventricle kind of sits right here at kind of an angle. We cut a slice like, prescribe a slice like that. We'll typically acquire several slices of the heart. We'll cut it like a loaf of bread. And each slice will acquire a movie for about 20 time frames. And that can vary plus or minus, but about 20 time frames per cardiac cycle. And so if y'all ever had an MRI before, they'll tell you to be really still when you're in the MRI scan. They'll say, look, be really still. You don't, if you move, they'll just scrub the scan, it'll take long. That's absolutely true. Heart's always moving though. It's actually moving in two ways. It moves with the fact that it's beating, of course, and pumping blood through your body. Also respiratory motion. As you breathe, that heart translates up and down in your chest cavity a little bit. So what we do when we acquire these MRI scans, we do two things. First of all, we do breath hold scans. We ask the patient to hold their breath about 16 seconds. And most people, even heart failure patients, can hold their breath for 15 seconds, 16 seconds. So that's one thing. We ask them to hold their breath, and that takes care of the respiratory motion. Also, we put ECG leads, sort of a limited ECG lead package on the patient, and we trigger off the R wave. Blip, you see, you've ever seen an ECG tracing. We trigger off the R wave when we sync the acquisition of the scanner with that R wave, and that allows us to get a series of frames of how the heart's beating inside the chest. This is the typical, this is the workhorse MRI scan. There are others, of course, but this is the most. And typically, when we say cardiac function, we're talking about volumes. You know, how much volume is in the heart at its maximum point, at its minimum point, how much blood is being ejected out of the heart in each cycle. That's generally what you want to know, because that has implications for several diseases. And the way you can do that, and I don't know if you can really see this picture here. It's done with what's called planimetry. Sorry. As I said, this is the heart here. We cut it like a loaf of bread. Each slice, we get a movie, basically 20 time frames of the heart through its cycle. We'll clinically, we'll contour the heart in diastole, which is this maximum volume time point, and in systole, which is the minimum volume time point. And if you draw a circle around the inner wall here of the left ventricle, and get the area of that circle, multiply it by slice thickness, that gives you the volume in that slice. And you do that with all these slices in the heart, you add them all up, and that's the volume at that time. You do it at 2 time points, you get a maximum and a minimum volume, or in cardiovascular terms, in systolic and in diastolic volume. And these are the parameters that you can use. And again, and you can get these from echo as well, but in diastolic volume, in systolic volume, stroke volume, that's the amount of blood that's ejected out of the heart. Ejection fraction, which is this stroke volume. Yeah, that helps with some of these images. Also, ejection fraction, which is the amount of blood ejected out of the heart as a percentage of the maximum volume. If you ever heard somebody say, well, you know, my parents in the hospital, their heart's at 40%. They're talking about ejection fraction. And normal ejection fraction is 60%. So hopefully everybody in this room, our hearts are ejecting about 60% of the blood in the heart every cycle. So these are the clinical parameters that are typically measured from a cardiac scan in their image, or they're calculated using this planimetry technique. Okay, so what we want to do, what we did in this project, and this happened a few years ago, right? This is, I guess, maybe at the very beginning or slightly before the AI revolution. What we wanted to do was we wanted to leverage these contours that were drawn typically by a cardiologist or a tech, depending on the group, end diastole and systole. So they only drew contours at 2 time points. Only 2 of those 20 time frames were used for computing these functional parameters. The rest of them were thrown away. We said we wanted to use those. I'll show you what we're using for it in a second. But we wanted to basically take those 2 contours and leverage them and use those to sort of, or we wanted to propagate those contours to all the remaining time points in the seating frame. So what we did that using non-rigid registration. There was no AI involved. This was a pretty mathematical technique.
Excuse me.
Yeah.
Can we share your presentation? So I can.
Oh, you have to share your screen. You can just see.
Okay.
Can you go ahead and? Oh, but you're going through.
Yeah, I'm sharing. I'm already sharing it to the projector, but you want me to share it to that thing?
Yeah.
Okay. Let me see how to do. Let me see if I can do that.
Oh, so they may have missed the previous image.
No, no, they can see it through.
Have you seen it through the camera?
Yeah.
Okay, do you want me to?
Yeah, so yeah, you can
Just
yeah,
plug
just
in.
plug in.
Okay. So is the connection USB-C or USB?
Um,
Is it this one?
yeah, it's like the one and then.
Yeah, yeah. Right here.
Okay. Right, there we go. Let me see it. I'm trying to drag it on there. Yeah, and then share.
The Windows box should be here. Is this it? Yeah. I was placed here more. Yeah.
Just. Yeah, you're good.
Not working?
Actually.
Oh, okay, we have to go in here and probably the PC here.
Oh, good gosh.
You got the screen on Zoom.
Yeah, sorry about.
All right. There's always some kind of AV issue.
Yes.
Now we got it.
All right, okay.
So.
So just to, I'll just briefly recap what this is sort of the basic workhorse sequence. It's a cine MRI. We get movies of the heart beating in the chest. And from this, and you get a stack of these. Here we go. You get a stack of these. This is called planimetry. Get a stack of these. We draw a contour here. At one time point, you get a area inside that contour, multiply it by the slice thickness. That gives you the volume of that slice. You add it all up and you get your slices. You get your volume for that time point. Do that at 2 time points. And from that, we can compute all these neat parameters. What we wanted to do was, instead of throwing away those 18 time frames, we wanted to leverage that. Let's take the contours that are already being drawn to compute this functional data and just propagate them to all the remaining time frames using non-rigid registration. And that's what we did. Again, this is not an AI technique. So this is a typical typical left ventricular volume time curve. It starts at 135 millimeters or milliliters. In diastole, this is the ejection phase. This is in systole. And when the heart contracts, it kind of rings like a rag. Okay, and then when it relaxes, it kind of snaps back with a passive recoil phase. And that's what you see here. And there's a diastasis phase, and then this little piece right here, that's when the left atrium contracts and squirts a little bit more blood into the left ventricle, fill it up to its maximum capacity, and then it starts all over again. So what we want to do with this technique, since we've got all these volumes, we want to measure these slopes. We want to measure the systolic ejection rate for late diastolic relaxation, late or atrial diastolic relaxation. And there are, we use those parameters in lots of clinical studies that we ran through our center. This is just an example of what I'm talking about. Those are the two contours that are drawn in systole, or excuse me, in diastole in the upper left. In systole is about a third of the way through the cardiac cycle, so that's about right here. And then from those contours, we propagated over to all the rest. And this paper came out in 2009, so it kind of dates us a little bit. These are we've also got a cardiologist to hand draw these contours, and each of these 20 time frames times probably 12 slices. So it took him a while, but let's see. I always forget which one is which because they're so close. The yellow one are the manual contours the cardiologist drew, and the green ones are the ones we propagated. So they agree really well. So this technique has really been a workhorse for us. It's allowed us to measure these parameters and get some insight of how the heart works in these pathological disease states that other groups can't do. This is an example of a normal versus a diseased volume time curve. That's the normal one. Different patient, of course, but it's a normal curve. This is somebody with what we call diastolic dysfunction. So this person has hypertension, and that means their heart wall gets really thick because they're pumping against a higher aortic pressure. And because that heart wall gets thick, it doesn't relax like a normal heart does. It doesn't have this nice elastic recoil. It has more of a slow relaxation. And that's a problem because the cardiovascular system's a loop. You can't relax quickly, then it just slows everything down, That's a problem, but that's the kind of thing we can measure with this technique. Okay, so, and there are other and also too, the whole just the initial segmentation process takes time. It takes those two time frames, about 12 slices per time frame. That's about 24 images. It takes you about 15 to 30 minutes once you're trained to do it. Maybe sometimes less once you kind of really get in the groove. But anyway, it's a very manual process. This is a problem where up until the AI era, we were just beating our heads against the wall as a community, trying to come up with an automated way to draw these contours. And it just, nothing ever worked. I mean, we could get to 80% accuracy pretty easily. Almost all the techniques can do that, but that's not good enough. 80% accuracy means you've got to go through the data set again and fix the contours that the automatic or semi-automatic algorithm screwed up. And if you do that, then you have to ask yourself, well, I might as well just go through the data set once, draw the contours manually and just be done with it. And some people are on one camp, some people are on the other, but that's still it's not a good situation. So there's been a lot of work with deep learning segmentation of the left ventricle and the right ventricle. That's what's being covered up here. This AI at AU logo. And then lots of groups have been working on this. We're not the only one. Most of them use some type of convolutional neural network and a UNet framework. That's the most common approach. And the two main issues at this point, and this has been going on for years, but the main issues are the size of the data of the training set. If you're working for Google and you're doing face recognition, you can train your network on billions of it. MRI and medical imaging, we never have that many images, ever. I mean, if we have 100 images, we're doing good. If we have 1,000 images, we're ecstatic. Okay, we're always fighting the battle of small data sets. There's a paper out by a group that uses the UK Biobank data set. The UK Biobank, basically everybody that gets an MRI in the UK, you sign a consent form, their MRI data gets plugged into this data bank. So there's groups that's gone out and segmented those 4,000 patients. And that's a really good paper. And they also use a UNET. So size of the training set's one issue. The other is domain generalization. You can imagine if you're dealing with small data sets, if you train on your data and then you try to use somebody else's data, it's not going to work as well. So that's another issue that we're trying to address in our research, and others have been looking at this as well. So we are fortunate to have a really nice data set here at Auburn. These are data sets that we've all labeled, my group has labeled by hand over years. We've got, and these are all different NIH funded projects that were funded to do something else, but one of the benefits are that we have all the segmented data that we can use for this work. Score data, we've got about 1,200 pages. These are patient numbers. Every patient has, again, probably 12 slices, 20 time frames, so probably 240 short axis images per patient. So that's whatever these patient numbers, multiply that by 24 or 240, that's the images. So score compass, you can see we've got about, I don't know, 1,500, 1,700, something like that. Patients worth of data that are labeled. And there are also some publicly available data sets. One's called the ACDC, and I forget what that stands for, but that's got about 100 patients in it that are labeled. You can also, once you validate your network, you can submit it to them and they'll run a test on some data that you can't see and give you a number for. And then there's some other data sets and that only have the left ventricle. The right ventricle, I haven't really talked about the right ventricle, but there's a lot of interest in the right ventricle. And most of the data sets are left ventricle. This is the deep, and what we're trying to do is we want to develop a deep learning method to automatically segment the left ventricle, right ventricle, and the myocardium, the muscle around the left ventricle, in these images. And this is basically our pipeline, which is pretty standard. We do some pre-processing. These images are typically not all the same resolution. You get images, particularly from another site, they're going to have a slightly different resolution to them. They're usually around 1.5 millimeters square in plane. So we do a resampling of the image to make sure it's a standard spatial resolution. We adjust the contrast. We also do some steps to do some data augmentation, move the image around, shift it, stuff like that. Then we crop it to where it's just the part of the image we're interested in. We do some normalization. That's MRI data. Basically has the absolute pixel value of an MRI image means nothing. The CT means a lot. But in MRI, images can have basically an arbitrary scale. So that's why we have the normalization step. Then we're looking at a different set of architectures, or UNET, REST UNET, HardNet, which is sort of a memory efficient dense net, and standard learning versus and also meta learning. So this is the standard UNET architecture. Y'all probably seen this before. Most everybody uses something like this. And in each block, we have a hard net, which is similar to this dense net you can see here. We've also looked at a REST UNET, which has 2 convolutions per block plus a shortcut residual block here. So we looked at several of these architectures, and these are sort of the ones that work the best. And so here's an example of what we get out of this. This is the raw image. This is after we pre-process it. And we didn't show you the data augmentation here. This is just a standard contrast, adjustment and stuff like that. This is the true label, and this is the left red here is the left ventricular blood pool. This is the myocardium, and from this we will get left ventricular mass. This is the RV blood pool here. So this is a more complicated structure. And this is the prediction. So you can tell they look pretty, this is a good result here. It looks pretty good. These are our results. And again, we're still in the validation stage. We haven't really said, haven't really figured out this is the network we want to use. We're still pretty much in the validation stage. When you look at these numbers, and these are dice scores, basically it's a measure of overlap between two segmentations. 0 means they're disjoint. 1 means they're totally agree, and 0 to 1 in between that. You look at these dice scores, and again, 80%, almost anybody can get 80%. Even our computer vision techniques going back in the day get 80%. So we need to get in the 90s to really get people's attention here. You look at the LV dice scores, they're all pretty much the same. So regardless of what network you use, you get about the same LV result. Same for myocardium, it's a little lower, but it's still consistent across these different architectures and learning strategies. RV is a little bit different. RV is a more complex organ to segment, even for a person. There's a lot more variability in the data. That's what we have. That's probably why the score is low. But all these results were trained on our data. And actually, this was a multi-site study here. So there's data from other sites in that study. It was trained on our data and validated on this ACDC data set. Came from another institution. Okay, so in addition to volumetric parameters, we can also do geometric analysis of the ventricle. Look at the heart shape, how it changes its shape in response to disease. Normal heart looks like an American football. It's kind of ellipsoidal with a pointy end. You see there. What we're interested in typically is curvature, which is a directional quantity. Also, regional quantity is going to be different here than is going to be the apex, for example. But once we have contours for all the slices, pretty easy to compute curvature. Just from the image header, you can tell where each slice is positioned in space. With the contour, you can render the contours up in 3D, put a surface to it, parameterized surface. On that, you can compute curvature in a straightforward manner. And what this is mainly used in a disease called mitral regurgitation. This is normal heart here. Normally, the heart, left atrium ejects into left ventricle. Left ventricle contracts, pumps, and the mitral valve here closes. All the blood goes out the aorta. That's the way it's supposed to work. That's normal. And somebody with mitral prolapse, or in this case, mitral prolapse with mitral regurgitation, this valve doesn't work properly. It leaks basically. When the heart contracts, instead of all the blood going out the aorta, then that goes back the wrong way. And that's obviously not a good thing. If you leave that untreated, you can go into heart failure and you can die of this. Although, hopefully you'll have symptoms before that and go see a cardiologist. There's two ways out there. If it's mild regurgitation, you can treat it with medicine. There's some medicines that can treat this. There's also surgical techniques which are for patients that have moderate to severe mitral regurgitation. The problem with the surgery, though, is nobody really knows when to do it, or it's difficult to tell when to do the surgery. You don't want to do the surgery too early because you want to give medications an opportunity to work. But if you wait too late, studies have shown that a lot of times it just doesn't work. So you've undergone a major surgery to your heart and not gotten any benefit out of it. In fact, it gets a little worse. So what we've been doing is using all these different parameters of shape and advanced functional parameters and things of that sort, using them in a machine learning framework to try to figure out, can we more accurately predict what the outcome of surgery will be in these mitral regurgitation patients. This is just a slide showing you what the images look like. This is a normal patient on the left, in normal LV, RV. You see the nice pointy end on the ventricle. This is somebody with severe mitral regurgitation. Basically, your heart gets a lot bigger, MR, because some of it's going the wrong way, so your heart gets bigger to compensate for that. And not only does it sort of dilate circumferentially, but this apex gets more rounded. That's one thing we found to be very important in these patients. This is just sort of, this is also, this was a study where we actually segmented the left ventricle, left atrium, right ventricle, and right atrium, all time frames. This was a really hard study to do. But one of the things we noticed from this study is the left atrium. Look how big it gets. This is the left atrium in an MR heart. Left atrium gets really big because, you know, it's a really thin-walled organ, and you're getting blood pumped into that atrium when it's not supposed to have blood being pumped into it, when it's supposed to be contracting and pulling the blood. So that's we can also do this contouring for all the other other three chambers of the heart as well. This is some work, and this is coming out pretty soon in Quantitative Cardiovascular Medicine. I won't go into detail here, but here are all the parameters that we can measure. This is like 37 parameters. There's really more than that. There's a lot more than this than we use. These are the ones we kind of focused on in this paper. We looked at random forest support vector machine XG boost, and also lasso, which is a regularized linear regression technique. And we did some analysis to reduce our parameters, figure out which the best model was. Random forest was the best model. And we figured out that these were the best features: left ventricular ejection fraction, sphericity index, and tells you how rounded that apex of the heart is. And systolic dimension, which is what's followed clinically, and this circumferential strain rate. I haven't talked about strains, but I'll talk about that in a few minutes. Anyway, we finally got a model, and then we tested it on some patients that were not used in this training process, but were asymptomatic. So these were mild, moderate, severe mitral regurgitation patients. And if you applied this, but we had all these parameters for those patients, and if you run them through this model, it said that 14 of these patients would have, you know, a poor outcome post-surgery. So that means that we think this has some potential. Obviously, we have a lot more work to do. We need to get a lot more data. We only have like 51 here and 49 here, where that's too small. We need to get more data, but the technique does show a lot of promise. And also too, notice that the linear technique didn't work at all. We tried this in other capacities, and linear models just don't work for this prediction application very well. This is mechanical function, and I'm running short on time. So this is the same slice that I showed you earlier. Same person, same slice. Instead of doing cine imaging, which is what standard MRI imaging is, we use this technique called tagging, where we actually go in and we paint with the scanner. We sort of paint this grid pattern on the heart. And we can do that by making a temporary change in the magnetic properties of the heart with the scanner before we acquire the image. If we paint this grid pattern on the heart and then allow the heart to contract and image moving the heart's contraction, this grid deforms with the heart. Again, this is not some sort of post-processing trick. This is the actual raw data. We can track this. We can look at the deformation of this grid and get really accurate measurements of how heart's contracting from a strain standpoint. Change in length per unit length of heart muscles as the heart goes through its cycle. And again, strains a tensor, 3D tensor. We measure the 3D strains. We can also have long axis images and tagged acquisitions of the long axis. We can measure strain in the circumferential, longitudinal, and radial directions. Heart contracts circumferentially, contracts longitudinally, and it thickens. The wall thickens radially during its cycle. So we can measure all three of those strains, and also compute principal strains if you want. But I won't really go into that. And this is an example of what we have. So we've developed a user interface. You can go in, load up the data, measure these tag lines, or segment these tag lines. This definitely needs some work, because this is sort of it's a semi-automatic process. The computer will get you close, but you definitely have to go through and fix tag points. Each point on that tag point is a measure of Deformation, we can render all of those up in 3D, put a deformation model to it. Once we do that, we can compute strain. And this is a strain in a normal heart here. This is circumferential, this is circumferential shortening strain, longitudinal shortening strain, which is usually lower than circumferential. This is somebody that's had a heart attack. So what happens with a heart attack, one of the coronary arteries that perfuse your heart is blocked by some sort of plaque. And if that region of the heart's deprived of blood long enough, it actually dies. So it doesn't really contract like the rest of the muscle does. So you can see here, the contracted strains just in general are not as strong or robust as they are in the normal heart over here. You see, particularly in this region here, it's red. Red is basically no contraction. Blue is sort of the maximum contraction. This is again pre-AI, but this was an attempt to do a better job of looking at the time evolution of strains. So just looking at a snapshot at their maximum point. Let's look at strains over time. And so we can do this with what's called HARP analysis. What you do here is you take a 2D Fourier transform of this image. You're going to get peaks, all right, because that's a periodic image. You isolate this peak and reconstruct an image of just that peak. And in this peak, you'll get basically two phase images in perpendicular directions, which correspond to the tag points over there. Right. And we've developed some techniques for unwrapping those phases and generating these nice unwrapped phase maps. And these are, each point in here is a displacement measurement. So we can do the same thing, render them up in 3D, put a deformation model to it. But instead of having just strain at a single time point, we can look at the evolution of strains over time. And this is an example when that paper came out, 2011. So this is a normal heart on the left. You can see the strains start out at 0, not where they should be. And as the heart contracts, it goes through this red, purple, or purple color to blue. This is a normal heart. This is somebody with pulmonary hypertension. This person has the pulmonary artery, which goes from the right ventricle to the lungs, got high pressure in it. So that means pressure in the right ventricle builds up. And so it's got this rounded shape versus the flat shape that you have in the normal ventricle. In fact, it's so high that it actually starts to press in on the left ventricle, which generally works at a much higher pressure. In fact, you can kind of see the flattening of the wall there. So, but in general, the strains here in this diseased heart aren't as robust as the ones in the normal heart. But anyway, this is we don't currently. There's not a lot of work by any group doing artificial intelligence or deep learning, machine learning, whatever. Segmentation of these tags. That's definitely an area of need. There's a few papers out, but nothing like there is for the contouring cine MRI data. But we've all the studies that I showed earlier that we have cine data for, we also have this tag data. We've got a nice data set. Once we yeah.
I'm not following this picture, how this is showing pulmonary hypertension. I don't get it.
Okay. So pulmonary hypertension means this is the right ventricle, left ventricle. When the right ventricle contracts into the pulmonary artery,
Yep.
goes to the lungs. If the pressure in your pulmonary artery is greater than 25 millimeters of mercury, you've got pulmonary hypertension. Normal pressure is around, I don't know, 5, 10, something like that, a lot lower than that. So, but because everything's connected, right? So if you have high pressure in your pulmonary artery, it means you have high pressure in your right ventricle. Typically, again, this typical heart, this is probably 120 millimeters of mercury over here, probably 10 millimeters of mercury.
Oh, you're saying it's pushing on the left ventricle?
Yeah, so this one's that. So
Okay,
this
yeah.
is, it's pushing on it. Yeah.
Okay, thank you.
So this definitely, we're not really doing any, we're not doing any work in this area, although it's on our list. And there are some other groups that are there's like maybe 1 or 2 papers on this area, so it's really kind of an open area work. On the topic of pulmonary hypertension, high pressure in the pulmonary artery, there's several different things that can cause it. One thing that can cause it is pulmonary arterial stiffness. Sometimes your pulmonary artery just gets stiffer. Some of that's just normal aging, but obviously if you have pulmonary hypertension, it's more than just normal aging. It's gotten a lot more stiff. So we've been working on some things in that area. And as I said, pulmonary hypertension means elevated pressure in the pulmonary artery. This is the right ventricle pulmonary artery here. Bifurcates into the right and left lungs. Now, the way pulmonary hypertension is diagnosed today is with a right heart cath. They actually have to stick a catheter up through one of your veins into your right ventricle and up your pulmonary artery to measure those pressures. So it's an invasive procedure, not something you want to do if you can get away with it. And it's obviously the gold standard for measuring pulmonary hypertension, but it's difficult it doesn't really do a good job of measuring pulmonary hypertension in its early stages, probably because in its early stages, people don't do the right heart cath. But still, that's an issue. So what we've done, and this is a technique we developed here at Auburn, it's called the velocity transfer function. What we do, this is the pulmonary artery here, bifurcating into the right and left branches. What we do is we measure across, we do a measurement at a cross section here, proximal to the bifurcation, distal to the bifurcation. And we do a technique called phase contrast MRI. Typically, MRI is a Fourier imaging technique. You actually acquire the 2D Fourier transform of the image. And when you do a reconstruction, you typically throw away the phase information. Just keep the magnitude of the inverse Fourier transform. But with this technique, some things are done differently. You actually keep the phase. If you do things the right way, each phase pixel here is proportional to blood flow through the image plane. And we can map each pixel to a specific velocity. So what we do, we draw a circle around this pulmonary artery here, each of the 20 to 32 time frames. We get a mean velocity for each point in this movie, and we get a proximal curve. We get a volume or a velocity versus time curve. It says flow, but it's really, I guess, we get a velocity curve that looks similar to that. And so when we do that at 2 time points, so an input and an output, and a pulmonary artery, which is similar, the aorta does the same thing, but a normal pulmonary artery is compliant. When the right ventricle contracts, it pumps a bolus of blood into the pulmonary artery, it's going to expand a little bit. And then when the valve closes and the right ventricle fills up with blood, the pulmonary artery will contract a little bit, keep blood flowing through the lungs throughout the entire cardiac cycle. So as an electrical engineer, I kind of see that as a low pass filter. So basically it has sort of a low pass filter effect on the velocity waveform as it moves this little section of artery. What we can do with this technique, if it's a compliant artery is going to have a transfer function looking something like this. This is what a stiff artery would look like. Again, the cartoon, they're a little bit different in practice. And so what we do is we take the output velocity transform or velocity curve, Fourier transform it, Fourier transform the input velocity curve, divide those two things together. That gives us an estimate of this transfer function, and we'll look sort of in this sweet spot here and get a measure of pulmonary artery stiffness. So that's the technique. Published a paper, and we also got some NIH grant money to investigate this further. We published these results in Journal of American Heart Association. And so here, the transfer function curves were sort of a normal. So what we did is we got 20 patients that were getting right heart caths anyway. And so in addition to the right heart cath, which is part of their standard of care, we did an MRI. And we got some seed money from a grant to do that. And it turns out some of them had normal pressures, and that's this black one. The normal people with normal pressures were like this. Transfer function for the people that were abnormal are here in red. And that was the VTF, velocity transfer function, our technique. That agreed really well with the same grouping of patients, but with pulmonary artery impedance, which is an invasive measurement. And that's the gold standard for measuring pulmonary artery stiffness. So we're very excited about that result. We use AI in two ways in this or machine learning in two ways in this area. One is, segmenting that contour, that pulmonary artery. Same thing we do with the ventricles. We train it's a UNet. I think, and we've looked at both 2D and 3D approaches. 2D is basically send each image in the network by itself. 3D, you stack them up into a 2D plus time, the 3D convolutions. That the 3D with the REST unit has worked the best. You can see these dice scores are a lot better than the ones before. So we can do a much better job of segmenting out the pulmonary artery than we could the left ventricle. And that's even though we have a much smaller data set to work with here. I mean, here we've only got maybe 70 patients to right heart cath patients to work with. And so it's a lot, it's really a problem with this data. But so far the AI segmentation is going well. Almost done. We're also using, instead of using, so the VTF as it was originally formulated was a very deterministic way of approaching it. Here's the output for a transform, it's an algorithmic way of doing it. So instead of, there's actually some issues with that approach. So instead we're starting to look at a neural network approach where we say, but here's our input and output velocity curves. Here are the parameters we measured invasively with right heart cath in these 70 patients. And obviously I'm skipping a lot of steps here, but then we get a parameter out of it that says this is related to the stiffness of the pulmonary artery. And that's really been very promising. And what we'd like to do is validate it, test it like this. We want to be able to say, well, these are normal people. These are people with pulmonary hypertension and COPD, chronic obstructive pulmonary disease. They're somewhere in the middle, which is what we'd expect. So we'd like to see a plot like this. This I obtained by cheating. I use my training data and all that. And again, it's not a result that I can publish or really do anything with, but at least it's a sanity check. I mean, if you can't get good results with it like this, you're screwed. So that's how we'd like to validate the results. We don't have like a parameter, single parameter we can look at to tell whether we're doing a good job or not. So what we're going to do for our validation strategy, because we have a really small data set, we only have like 70, I think 77 patients with right heart cath data. What we're going to do is we're going to do 5-fold cross validation, which is pretty common. And then we're just going to do like 100 iterations in that 5-fold cross validation. This is just an example. 5 patients, 5-fold, 3 iterations. This is just a full example. That's how we're going to get that's our plan for getting a reasonable publishable result out of a really small data set. So that's really it. Just in summary, we looked at ways of quantifying function and geometry, mechanical function, and pulmonary artery stiffness. We use machine learning in a good number of these. The only exception is the mechanical function, where that's an area of need, something definitely on our list, but we haven't done that yet. So I'd like to thank my collaborators, students, sponsors. And that's it. This is our new 7T, which is being installed now. So as I said, turns out 7T is not really that useful for cardiac imaging. There are some things you can do with cardiac at 7T, but kind of stuff I'm talking about, it's really better at 3T. And that's what we do so we use our 3Ts. All right, that's it. Any questions?
I've got questions and comments. One is a personal interest. First of all, sure, the science of pumps is very interesting to me anyway. And so, but I just recently had one of these procedures at the new medical center. 60 years old. They said, you need to go get one of these calcification something.
Well, that's a CT scan. Yeah, yeah.
And I don't know how that's different, but when they talk about stiffening, where all my numbers were 0, which they said, that's what you want.
Yeah, exactly.
But when they say stiffening and an old fashioned term would be like hardening of the
Yeah,
artery.
that's exactly the same thing.
Relate to calcification and stiffening and, or what does that have to do
Right.
with what you're talking?
Okay, so what they were probably talking about at the clinic was stiffening and hardening of the aorta. I was talking about stiffening and hardening of the pulmonary arteries. That's what comes out of the left side, which is really the more important part. There's obviously the right side is important too, because everything's a loop. That's the difference between what you went through and what I was talking about.
Okay.
Number one. Number two, calcification is basically what is one thing that causes the stiffness. And to evaluate that, they use a CT scan, which involves X-rays and ionizing radiation, not MRI. MRI isn't very good. I'm not able to measure it at all.
So that, even though it looks like that, I lay down, they slid me into this donut machine.
Yeah, it looks similar. It's probably skinnier. It's probably a donut about that thick, right?
Yeah, but that's a different type machine.
Yeah, MRIs are, even a small MRI is probably 6 feet long.
That's where the whole body goes.
You're right.
in there.
Yeah. You got a CT scan.
So you use a lot of neural networks, obviously, like image data, good thing. But I was wondering, like, how did you like design the structure of the neural network? Like, how many hidden layers and stuff? How do you like determine that?
That's a good question. That's my knowledge. There's not a whole lot of theory to guide you there. I mean, there are guidelines and sort of rules of thumb and stuff like that. But basically, we just looked at the papers and tried to copy what other people have done, start from there, and then see where we can make improvements.
And then another question, you said that there's not a lot of data for this problem. So is there like a way to like generate data, like simulate data for this problem? Or
Yeah, and a lot of people looked at that. I'll be honest, I'm a little skeptical of that because, simulating data and data augmentation only works if it looks like what a real data set.
True.
And, while rotating and shifting, that's realistic. And you can do a good job of that, right? But when you start trying to simulate, a beating heart and how it forms and stuff like that, I'm not sure you really get something that looks realistic. At least not to this point. That may change in the future, but the ones I've seen so far have not really convinced me they're useful.
it's like, I don't know, I've done some research in this area, like GANs, like general adversarial network.
They have you the
And you
adversarial
can
network.
simulate,
Yeah.
So that.
Yeah, that's a lot of the techniques have used that.
Mhm.
And again, I'm just a little skeptical because if it doesn't look like real data,
Sure.
you're not helping yourself.
Right.
And it's really hard and the heart's contraction can be really complicated, particularly in disease states.
Mm.
And so that's the basis of my skepticism, but that could change, moving forward.
Any other questions? Oops, we have. Okay, this is from Dan E.
Oh, okay.
And question is, how will the 7 Tesla provide new capabilities for diagnosing disease and creating new research problems or data sets?
That's a good question. So the 7 Tesla, we've had a 7 Tesla. We got our first 7 Tesla 2012. So we've had it for about 10, 11 years. That was a research only device. So it wasn't FDA certified. We could only use it for research. We could image people with it, but it was only for research. We couldn't do clinical imaging. This new 7 Tesla, it will be FDA certified. We will be able to image people clinically. We're hoping. The plan is when you have somebody that's already in the scanner for a clinical scan, you can consent them and they'll maybe agree to the 10 minutes extra in their scan to collect some research data. And a lot of research groups do that. For example, in Columbia, they do a lot of that type of thing. It's worked out really well for them. But the 17 is mainly brain imaging. For the heart, It turns out there's some technical reasons why it's difficult to image the heart at 7 Tesla. What you do at 7 Tesla in the heart is what we call spectroscopy. We're actually looking at the biochemical composition of the heart. And we can actually look at phosphorus metabolites in the heart with 7T. That's what we do at the heart at 7. But everything else at 7T is brain. We do brain a little, again, 90% brain, a little bit of heart, a little bit of knee. It turns out the knee is really good at 7T as well. 7T is really good for imaging small things in the body, like brain, knee. We can measure ankle, but I don't think there's a whole lot of people doing that. Does that answer your question? Yeah.
He says, thanks a lot.
Okay, I'll think that's a yes.
Any other questions? If not, thank you.
It's because to me, this kind of stuff is always kind of scary.